Hello, this is GunFun ZS, here for a Reloaders Coffee Chat on what I think is an interesting subject. Now, a thing you should know about me is I pretty much always got coffee with me, usually in a Contigo sippy cup, because I'm clumsy. So, anytime you're chatting with me, it's a coffee chat. So let's talk about an issue that came up with me over the course of the last couple of years of developing loads. My good friend Fortune Cookie 45LC had some really nice discussions about concepts like load density and reducing your standard deviations, and that caused me to get a certain idea in the back of my mind. Then later, I was working on a different project and getting some really good input from a guy who goes by Della on 300 Black Talk and some other forums, and I realized that my idea was actually wrong. So let's talk about what I had wrong. Most of the time, we're looking for a balanced state, because balanced to our human mind seems to be the most stable. But this is actually the opposite of true. Balanced isn't the most stable. Small changes we expect to make small incremental differences. Add a little bit more, take a little bit more away, and you get a little bit more change. But the thing is, most things in nature aren't really incremental, and sooner or later it pops. If this was a good quality scale, it'd be like that already. So really, in nature and in science, the most stable state is not a balanced state, but something that's very imbalanced. Not only will a small inevitable change not make much of a difference, even adding a few on this side isn't going to change that state of balance. I can add a lot on this side before it gets to change. If you really want to make something stable, you make it all one thing or all the other. And this is what my discussion is about. We're here to avoid threshold states. So let's talk about that a little bit. There's always going to be variation. We can't eliminate it. We can make the variation as small as we can, but we not only want to minimize the variation itself, but the effects of the variation. So, for instance, a tenth of a grain one way or another will make a bigger difference in some conditions than in others. I used to play a lot of paintball, and I'm a techie guy, so of course I got techie with that too. There were a lot of smart and innovative people in paintball, and one of the things that we found was when we had consistent paint that was a good fit to our barrel, we got much more consistent accuracy. And that totally makes sense, and that's very intuitive. And the conventional wisdom of smart people was that what you wanted to do, since you couldn't control the diameter of your paint constantly, was to change the diameter of your barrel to match the paint that you could obtain on a given day. So most of us who were serious about playing had barrel kits with varying diameters. And the standard method of choosing the right barrel for your paint of the particular day was to blow gun it. You would stick a paintball in the barrel and blow. And if it would blow out without too much difficulty but wouldn't fall through the barrel, that was your best place, right? Except for then we got scientific about it and tested it in this form called Punkworks and did some pretty large scale testing. And what we found was What should have been obvious to us, which was what we were thinking of the best place, was actually the worst. What we needed to be was always falling through the barrel, so there was always blow-by, or always a tight seal in the barrel, so it's always compressed. Those are the stable states. Right in between, where it's sometimes blowing by and sometimes compressed, is the maximum inconsistency. So a lot of times conventional wisdom and the way our brain wants to think about things is wrong. And so let's look at some of those. One of those that I think is in that category is what we'd call 100% load density. I think 100% load density might be the worst possible load density. And I'm really looking forward to Fortune Cookie's thoughts on that. We could call this whole discussion be an always or a never. Sometimes is terrible. You don't want never or sometimes or maybe. You want definitely or definitely doesn't. We could call this get off the fence or be a fish or fowl. One thing or the other, but never in between. Now, taking this concept a couple steps further, what we'll see is that while we tend to think of things in incrementally progressing trends, some things cross a threshold or boundary state where a whole other set of rules applies, and the behavior quits being predictable according to the old rules. And so we're going to look at a few of those that relate to shooting and reloading. So here what we're going to look at is a made-up cartridge here. Let's say this is something like 30-06 or maybe 7mm belted made-up. Anyway, let's look what would happen basically if we consider two variables. We'll first start looking at increases in velocity as we add powder. Starting out at no powder, we'd have terrible standard deviations because there's not enough case capacity to get a stable burn, right? As we start to get 70-80% load density, then we'd be in this zone where suddenly it starts to behave fairly consistently and predictably. We'd have standard deviations that would give us kind of a fat line, but the line would start getting skinnier. And adding a little bit more powder would get a little bit more velocity, a little bit more powder, a little bit more velocity, and so on. And we'd reach this point where the standard deviations are tiny, and that might be a really good accuracy node, not thinking about barrel harmonics or whatever. This would be a place where your velocities would be very stable. As we continue to add powder, eventually we would touch the base of the bullet. Now, increasing the powder may or may not increase the velocity very much. It'd be a little bit like a bell curve. And if we increased it way up, we'd find diminishing returns where we start getting bad standard deviations again, where we're finding fast bullets and slow bullets and fast bullets and slow bullets from the same amount of powder. And so that's a bad situation, but there might be a low standard deviation node here and a low standard deviation node here on either side of compressed load or not compressed load. However, what you tend to find is that there's this sort of stable bell curve, or at least a section of the bell curve looks kind of linear, that we can predict what's going to happen as far as the pressure curve. However, when you cross the compressed load threshold, it suddenly behaves on an entirely new logic. The curve increases radically. It may be steady or it may be erratic. So, if this is the pressure threshold where the gun blows up, adding one more grain of powder is a very big difference. And if we say we are plus or minus 0.1, being over here plus or minus 0.1 grain isn't that big a deal to our outcome of either impact point or gun blows up, not blows up. Over here, plus or minus 0.1 grain might be a huge difference in the change we get. And maybe right here might be okay. So this is where you kind of have to consider for multiple factors. There are several things on our chart here. So I've got this in terms of always, never, and sometimes. And sometimes things can be good in each of these categories or okay. And sometimes it's good in both the always, or both the never and the always. So let's look at one thing. So non-compressed load can have stable behavior. Compressed load can have stable behavior. In between where it's 100% load density is right where a small variation in change is sometimes compressed and sometimes not. So we can be okay here and we can be okay here, but we don't want to be here. Another one worth looking at here is the next factor, which is all powder is burned in the barrel or every load has unburnt powder. So let's look at this made up graph here that I've got, which would be percent powder burned over time. If we see time is this axis and percent powder burned is this one, you'll notice that initially, just as the primer goes off, it's not particularly consistent, and as time goes on, more of the powder gets burned. Eventually, all of the powder will be burned. And if you give enough time, say 2 minutes later, we know all of the powder for sure burned, right? Most of this stuff is happening in milliseconds, and I believe for most rifle calibers, the time in barrel is either 2 milliseconds or 2/10 of a millisecond. So we'll assume it's tenths. But let's say this green line right here is, say, 0.8 milliseconds, and then this is 2 milliseconds, and this is 2.4 milliseconds, or 2.2 milliseconds. Something along those lines. You get the idea. You'll notice that the percent powder burned is a pretty steady curve that starts to flatten out at the top near 100%. It's like a line approaching zero, you know? 100% burned. However, some loads will end up being fully consumed in the barrel, and some will be not be fully consumed in the barrel. Your problem, and since barrel length basically correlates very directly to powder burn time, where you cut off the barrel for a given load will affect whether it's on one side of the threshold or other. All the powder's burned, not all the powder's burned. So in this area, the curve looks almost like a straight line. It's very predictable. There's very little change with a minor change in time. So if we were to say have a 7.62 by 54R with an 18-inch barrel, maybe you have 90% of the powder is burned in this neighborhood. But it's a very consistent 90% of the powder burned, a consistent amount of energy. Or you give it a 24-inch barrel, and for sure all the powder's burned, and it's pretty consistent, although the variation in the quality of the ammo will make this one a little less consistent than that one. But your worst case scenario might be a 20-inch barrel, where a significant number of the cartridges have powder fully burned in the barrel, and a significant have it fully burned outside the barrel. So you'd have very big incidents of high vertical stringing and weird barrel harmonics. And this is why if you're looking at things like .308 rifles, there's people who swear by 24-inch barrels for accuracy and other people who swear by 18, and kind of somewhere in the middle tends to be the worst case scenario. Or you change your powder and suddenly you're getting good results because you moved that burn threshold to here or to here. Anyway, that's the idea to consider. So going through the list a little bit more, if we look at very low load density, you can see that we get in an always or sometimes state. Some powder is always in contact with the primer, or the powder is never in contact with the primer, or slosh where it's intermittent. Both of these are bad, but the middle is worse. Next one would be the primer is never hot enough to fully ignite the powder, or the powder is always hot enough to fully ignite the powder. And then in between we have weather sensitive ammo, where you probably either want to change powder or maybe switch up to a Magnum primer. For me, it's probably going to be change powder. Now, we can also look at this as for whether your lube is effective or your method of application. All projectiles are coated or none of the projectiles are coated. I switch those columns, and in between is patchy and intermittent. That's going to give you inconsistent performance. You're going to be frustrated. or not enough energy in the load to cycle the gas system or work the compensator, or intermittently working the compensator or cycling the gas, and always doing it. For these, we probably want the always instead of the never, and the in the middle would be just frustrating. We'd have an unreliable gun or inconsistent behavior on your follow-up shot. The next one would be brass never overpressured, or chamber, you could say too. Brass is sometimes overpressured, and brass always shows pressure signs. Now this is one where we are okay with some loads, like 5.56 brass tends to show pressure signs just about every time, but it's okay because it's consistent. And 223 brass never showing pressure signs is fine too. Where you gotta worry is when you're seeing you shoot a string of 20 shots and you pick up your brass and you go, some of these primers look flat and the other ones don't. That tells you that there's something really wrong, such as powder slosh or inconsistent burn, or maybe you're in a semi-compressed state, and that you've got something on the edge of a threshold and you need to move it to one way or the other. We're okay with always if it's mild for the pressure signs, and we're okay with never for the pressure signs, but sometimes is bad. See also round, sometimes chambers. Get that case mouth diameter down or something, but sometimes sucks. Obviously, the gun never blows up is always better than the gun always blows up or gun sometimes does. We can also apply this to how we use a load. I can never expect to hit the vitals of an animal that I'm shooting at this range, or I can always expect to. And I think most of us would say that I can always expect to is an ethical shot, and most of us are smart enough to not do the never, but we tend to get ourselves in the trouble when we are in the sometimes range. Another factor for loads of bacon would be the bullet never expands at this velocity, or it always does, and the in-between is where you're frustrating and you need to get on one side of the threshold or the other. Okay, I'm going to move on from that, but I'm sure you guys can add some really useful threshold states to that. Now let's look at our next idea. Remember, we do have tolerances stacking, so the more things you have near a threshold and the more things you have to consider, the easier you have a chance of something getting on one side or the other of a threshold you don't want it to do. This is what I learned from Dellett. I was working on developing some 300 blackout loads, and he is probably the expert on 300 blackout load development. And one of the things that I learned looking for how to make 300 blackout work in supersonic cast bullets was that most of the commercial powders and the popular powders had pretty predictable performance curves. Add a little bit of powder and you get a little bit more performance. Some of them had more consistent standard deviations than others, like H110 was pretty predictable, and when you cross that threshold of it's compressed or it's not compressed, you'd see the velocity jump up and the pressures too, but it was still a nice, pretty tight line as opposed to velocity is all over the place. That's pretty nice. Now, there was a powder I was interested in, which is CFE black, and several of the people there were frustrated, particularly including Dellett. What they noticed was that loading this powder in uncompressed state, it had extremely erratic standard deviations. You would get velocities way low, way high, increased grain, way low, way high, just all over the place. You could plot a trend line in the middle of it, but looking at it as a skinny line sort of fools your brain into thinking there's a more consistent trend than there is. Really, if you want to think about large standard deviations as big fat lines versus nice tight lines, that gives you an idea. So it was steadily increasing as you increase the amount of powder in the case, but it was far from consistent. It was very unsatisfactory, and they also noted it was a dirty burning powder. However, one of the things that Dellett very cautiously informed me and shared a bunch of interesting data about was that it suddenly stabilized once you got it to compressed. That you'd suddenly get a nice, clean, steady line that was predictable and steadily increasing, and frankly had low pressure signs. Obviously, you guys know about how to take compressed loads seriously. We know that not all powders behave the same once they cross that threshold. Some of them would be steady on this side and very erratic on this side. But I think this is a great case study for it. Now, most of the reloaders in the 300 Black Talk forum concluded that it wasn't worth bothering with CFE Black. My conclusion was, actually, it's pretty amazing, and there's a very similar powder, Lever Evolution, that's also worth considering. And why it's amazing to me is, while if you compare it to the H110 that has this nice predictable curve, if these curves are pressure, you actually get it like this. For a given velocity, if velocity is constant, for the same velocity, this one, the CFE Black, is getting that velocity at a much lower pressure. And while you do have to pay attention to the aspects of compressed load, if you're making sure they're always compressed load, and you're watching pressure signs, you can get a functionally pretty accurate bullet with a cast lead bullet without having to have a hyper hard brittle bullet. Like in the, say, 24 to 36 Bresnell range, you can have jacketed velocities for a 115 or 120 grain bullet, and that's much more doable with a powder like CFE Black than H110, where you get in the top grain or two of their load data where it becomes compressed. The pressure is up high enough that you'd need like a 36 Bresnell hardness bullet, whereas this is in the pretty doable 24 to 30 range for the same velocity. So given those choices, for me, I choose this powder. And incidentally, both of these have enough power to fully cycle an AR, which there's plenty of other powders that are great on all of these things, but don't produce enough gas volume early enough to cycle your AR. So they're wonderful for a bolt gun and terrible for an AR. Our basic conclusion is we want to know whether we're near a boundary state and which side of that state it makes sense to be on. And if we're getting inconsistent results with something, odds are we're near one of these things. And that's a sign that we need to do some more work. Sometimes the biggest number is not our best result. Sometimes 100% is not our best result. Let me know what you guys think. I'm really looking forward to the rest of the discussion. I'll do my very best to comment or to reply to any comments down below. Thank you. GunFunZS out.